Hello, is this working? Okay. Thanks for coming. Interesting topic today. This is geoengineering. So this is something that if you haven't heard about it so far, you are going to definitely hear about it because there's more and more discussion about using geoengineering to address climate change. It looks like we're not able to cut CO2 in the way that we need to, so more and more people are talking about geoengineering, and people have been studying geoengineering, and there are definitely pluses and minuses. So it's going to be interesting to hear your perspective here. So our speaker today, I've got some notes here so I don't forget. Our speaker today is Stephen Warren. He's an emeritus professor of atmospheric science and earth and space science from the University of Washington in Seattle. So his research interests in the interaction of solar radiation with snow, clouds, and sea ice, and how that interacts with climate, hence the talk here. And he's carried out fieldwork in the Arctic and the Antarctic. He's taught classes in climate, atmospheric science, radiation, glaciology. I do have my glasses. I can look at I don't know why I'm doing this. Okay. And scientific writing. He's highly cited. He's a member of the American Meteorological Society, the American Association for Advancement of Science, and the American Geophysical Union. And for the past month, he's been visiting our department, hosted by Professors Regina Hock and Trude Storelma. So I'll hand the microphone over to him. After the talk, you'll have a chance to ask questions. We're streaming this. So that means we'll come around with a microphone and hand you the microphones, ask the questions into the microphone, and then we can get it all on tape. Okay? So.
Okay.
Take it away.
Yeah, so I'm today asking a question. Can geoengineering preserve Arctic sea ice? And to answer that question, I've worked together with Melinda Webster, who's also at the University of Washington. So what is geoengineering? It means engineering the earth. So one category of geoengineering is engineering the climate by way of solar radiation management. So that means to counter climatic warming by artificially reflecting some of the incident sunlight back to space to keep the earth from overheating. That's one category of geoengineering, and there are two leading ideas for global geoengineering, in other words, affecting the whole Earth. One is to spread tiny transparent particles of sulfate into the upper atmosphere. That's called stratospheric aerosol injection, and it's meant to mimic the observed cooling by volcanic aerosols. So, for example, of the well-studied Pinatubo eruption in 1991, it caused the global average surface temperature the following year to be lower by 0.5 degrees. And that agreed with what had been predicted for it. The other idea for global, for solar radiation management is marine cloud brightening. So spraying tiny droplets of seawater from the ocean surface, they'll evaporate and make little salt particles, spray them into the humid lower atmosphere. Then water vapor condenses onto the sea salt particles to make bright, long-lasting clouds. And that was motivated by this sort of satellite picture, looking down on the Pacific Ocean and seeing these tracks, which are actually where ships were passing. The ships are emitting, their exhaust, and particles in the exhaust can collect water. So where a cloud was going to form anyway, or is forming, there'll be lots more particles where the ship went. And a cloud of many small droplets is brighter than a cloud of a few large droplets. So that's the idea of that one. That's sort of an introduction to the global scene. But instead, my title was about sea ice. I'm specifically going to look at sea ice. So what is sea ice? Sea ice is ice floating on the ocean formed by freezing of seawater. And the maximum thickness is a few meters. So the geoengineering of sea ice, and we're now getting more specific. This talk is not about global geoengineering. We're instead considering regional geoengineering limited to the area of the Arctic sea ice. Well, where ice occurs on the Arctic is on the left that's the situation at the end of winter in March. So the ice covers the entire Arctic Ocean, also some marginal seas, Hudson Bay, the Bering Sea, the Sea of Okhotsk, and then isolated from that, there's the Baltic Sea, the Gulf of Bothnia, and then by the end of summer in September, the ice reaches a minimum. It's gone from all those marginal seas. It remains in the central Arctic. And this picture actually is from around 1980, and this is no longer the case. The ice is smaller than this in September. And here's a plot showing the decline of the minimum ice extent. So it was 7.5 million square kilometers at its minimum in September in 1980, and it's declined, so it's now about 4.5 million. Now, in contrast, this is what the Antarctic looks like. On the left is the situation at the end of winter in September. The ice has grown out in all directions from the Antarctic continent, a very large area. And then, but by the end of summer, in February, it's all melted away, almost all. So different than the Arctic, but it's sort of what the Arctic is becoming, more like the Antarctic. And in particular, what the Arctic ice now is short-lived. This is a plot showing the ages of the ice since 1985, and the black one is the fifth-year ice that's lasted at least 5 years, some more than 5 years, and that used to be quite dominant in the residual ice at the end of summer, and it's quite thick. But now there's hardly any ice that's that old, and first-year ice that just grew in one winter and then melts away in the summer, is more dominant. And because of that, we've lost, yes, the older ice is thicker. And so although the Arctic has lost 40% of the area, it's lost 75% of the ice volume. Okay, well, engineers look at this plot and they think there must be a way to stop this. So there are proposed ways to stop it, and there are two categories of geoengineering schemes to preserve Arctic sea ice. You can either increase the growth rate in the winter, make it grow faster and thicker, or reduce the melt rate in the summer, so more of it remains at the end of summer. So the first one, increasing the ice growth rate in the winter. Well, the problem that the engineers see it is that sea ice thickens in the winter by freezing to the base. And the latent heat released by freezing then must be conducted upward through the ice, so the growth rate diminishes as the ice thickens. And the proposed solution is pumping seawater from below onto the upper surface, or spraying it out so that it would fall out onto the upper surface. As in the winter, then it'll freeze there. And that idea is actually now undergoing field tests, or it was last month anyway, in Arctic Canada. It's called the Real Ice Project. It's run by the Center for Climate Repair at the University of Cambridge. There's a paper soon to be published evaluating geoengineering for the polar regions, and the title is Safeguarding the Polar Regions from Dangerous Geoengineering. They considered 5 main categories of geoengineering in the Arctic. This was one of them, and they concluded that ice growth by spraying seawater on top is judged wildly impractical because of the large scale that would have to be applied over to be significant for climate. Now, I think it could be useful locally, just in a little bay in town, to maintain the ice cover on a narrow bay in villages so that you could walk across to see your neighbors. At that scale, it probably would work, I think, but it's not feasible for climate. And then the other category is reducing the melt rate in the summer. So there, what's important in the summer is the sunlight that's getting absorbed by the ice. So you want to reflect it away. So you have the incident sunlight, the reflected sunlight. The fraction reflected is what's called the albedo. It comes from a Latin word albus, meaning white, the same root as the Alps. And it it's the fraction reflected. So snow is the brightest. It reflects about 80% of the sunlight. Water, only about 7%. Forest, 10%, and so on. Now, so the way that has been proposed to reduce the melt rate is to spread white powder on the Arctic to raise the albedo. And that's the proposal that I worked on assessing, that specific proposal. Have any of you heard of this idea? Okay, 5 or 6 of you. Yeah, good. But before we continue, let's go back in time, because geoengineering proposals to alter surface albedo have a long history. 50 years ago, there was this paper in Journal of Applied Meteorology, Weather Modification by Carbon Dust Absorption of Solar Energy. So the idea was not to spread white powder, instead black powder. And this idea was to, yes, the solar absorption potential of carbon black dust. It could speed up springtime snowmelt. And Professor William Gray at Colorado State University included this diagram, figure 5 of his paper, showing how carbon dust would be generated and dispersed from a jet aircraft. You could fly this over the Arctic, you could melt the snow. Now we have the opposite concern. We're no longer trying to do this. This never did happen on a large scale, but back then that was proposed. Instead, we want to preserve the ice. Okay, so first we need to understand some properties of sea ice and solar radiation that are relevant to the geoengineering proposals. So I'll start out with how the ice grows and then how it melts. So when the ocean surface temperature drops down to the freezing temperature, which is -2 for the salinity of seawater, then instead of any further cooling, it loses heat by freezing. And small crystals form in the water column, and they are just loose and floating independently, but they damp the smallest waves, and so they appear, you can see that they change the appearance. So it kind of looks like an oil slick, and it's called grease ice. Then these crystals clump together into little clumps, maybe a few centimeters, which then clump together into larger clumps that are called pancakes, maybe a meter or half a meter across. They bump into each other. Eventually, they'll freeze together. That happens if there's significant wave action. On the other hand, in calm water, you don't get pancakes. You instead get nilus, which is a Russian word. It's a flat sheet of new ice forming in calm water. Within a few days after the nilus forms, it'll acquire a snowfall, and so then the albedo is more determined by the snow thickness than the ice thickness. Also, frost can form deposit on the nilus and brighten it by quite a bit, like can raise the albedo by 0.2 or 0.3. But then all winter it's growing in the dark, and when the sun comes up in the spring, you typically have a meter of ice and then maybe 30 centimeters of snow on the ice. So this is a typical scene in April, right about this time of year in the East Siberian Sea. And now we get to the melting process, and there's a big difference between the Arctic and the Antarctic. The Antarctic sea ice melts from the bottom because of a greater heat flux from the ocean, and it remains snow-covered as the ice thins. Whereas the Arctic sea ice, it's the snow that melts first. It melts from the top down. First, in June, you have melting of snow that forms melt ponds, little puddles of the meltwater that collect in the low points. Then in July, you get melting of the surface ice and melting of ice below the ponds. That causes the ponds to enlarge. In August, as the interior of the ice warms, the brine pockets in the ice enlarge and interconnect, forming vertical channels, allowing the ponds to drain. So this is a typical scene of melting ice in the Arctic summer. You have two types of surface there, and the white surface there is drained white ice. It is not snow. It looks like snow, but it's not formed from snowfall. It's formed by freezing of liquid water, but it has this top 3 centimeters that's called a surface scattering layer. It has quite a high albedo, not as high as snow, but about 62%. And it's because the grain boundaries in the ice melt under the influence of sunlight, so it has a texture something like coarse-grained snow and looks like coarse-grained snow. And this darker scene is the melt pond. Its albedo is about 25%, whereas open water is only 7%. The reason it's higher is because these ponds are shallow, so the ice underneath is reflecting some sunlight and adds to the albedo. We can break the year into 2 seasons, the growth season and the melt season. And they correspond pretty well with the dark season and the bright season. The dark season is the autumn and the winter, October to March. This is for 4 different latitudes, the solar radiation reaching the surface of the Arctic Ocean. So you see it's hardly any, comes in the autumn and winter. And in the spring and summer, there's almost 200 watts per square meter. So that means that what's relevant for the mass budget is different. In the autumn and winter, it doesn't matter what the albedo is. It's irrelevant because there's hardly any sunlight to reflect. What matters is the conductivity, and the snow can reduce the conductivity, and the air temperature, whereas in the spring and summer, the albedo is what's important. Actually, in both seasons, the ice motion is relevant and the open water fraction. Because the ice motion breaks the ice, ocean currents and winds can cause cracks to form and expose open water. Ice flows can break and collide, forming rafts and pressure ridges. Let's see if I can, there's a ridge, there's another ridge. So that's the kind of thing you get when 2 ice flows collide. And then what the open water that is formed when ice breaks is called a lead if it's wide enough for a ship to go through. This is a ship captain's term. If it's wide enough for the ship, then the captain says, okay, it can lead us through the ice. And the leads, they absorb sunlight, and some of that absorption of warm water, the warm water resulting, can go under the ice and help melt it from below. Now, what about snow? The snow starts building up. So this is the snow depth over the course of the year, starting in August. So it starts building up in September, reaches a peak of about 30 centimeters in May, and then rapidly melts in June. And the effective snow cover on the mass budget, as I've said before, in autumn and winter, the albedo is irrelevant. The effective snow cover is to insulate the surface, slowing the ice growth. In spring, the snow keeps the albedo high and delays the onset of melting. Okay, with that introduction, now we're going to come to geoengineering. And this is the proposal we're criticizing. It's what's called the Arctic Ice Project, led by Leslie Field, who's the first author on this paper, called Increasing Arctic Sea Ice Albedo Using Localized Reversible Geoengineering. What they're using are hollow glass microspheres. They call them HGMs. I'll just call them glass bubbles. They're tiny, radius of 32 microns. The wall thickness is 1 micron. And I met Leslie Field at a conference, and she encouraged me to stick my finger into a vial of these glass bubbles to see how light and fluffy they are. And yes, indeed, they are a white powder, very small. The manufacturer lists numerous industrial uses for these glass bubbles. So they are manufactured, they're available commercially. They also have some warnings, safety and environmental concerns. They tell you to avoid breathing the dust and avoid release to the environment. Well, we'll come back to that later. Yeah, there it is. Yeah, we will. Now, I had been avoiding the topic of geoengineering myself, but I got pulled into it. Leslie Field's paper was published in 2018, but we were unaware of it until 2021. What happened in 2021, the Geoengineering Modeling Research Consortium at NCAR in Colorado asked me and Melinda to evaluate the method. So our job was to compute the radiative forcing that could be achieved by spreading these glass bubbles onto the Arctic Ocean. Now, what that paper by Leslie Field reported two main things. They reported laboratory measurements, the radiative properties of layers of different thicknesses of these glass bubbles. And then they did experiments on bare ice. They went to a frozen pond in Minnesota and measured its albedo and then sprayed the glass bubbles over it, and the albedo rose from 25% to 50%. So that looked encouraging. But our job is to quantify what could actually be accomplished with the glass bubbles on the Arctic Ocean. So to answer that question, we'll consider seasonal cycles of solar radiation, snow cover, sea ice type, surface albedo. But just before we do that, just think about it. The new thin ice is dark, and so the glass bubbles can brighten it. But when does it occur? It occurs in the autumn, when there's very little sunlight. Whereas in the spring, there's lots of sunlight, but then the ice is covered with snow. Deep snow, whose albedo is already high, so it would be hard to increase it. Okay, so then where the glass bubbles could be most beneficial is to be spread over, well, there'd be three criteria. First, you'd want a low albedo surface so that it's easy to brighten it by spreading the white powder. Secondly, you'd want it to cover a large area so that it is relevant for climate. And third, should be in summer when there's plenty of sunlight to be reflected. And there's one surface type that satisfies those criteria, the melt ponds. However, on the melt ponds, the glass bubbles will be blown by the wind over to the edge of the pond and clump there. That's what Leslie Field's group observed in the pond in Minnesota after the ice melted. They got blown over to the edge. So we're going to dismiss the melt ponds and compute the radiative forcing over all the other surface types. And there are many surface types. We've listed 8 of them that cover most every possibility. And I'll just go through them one by one. Some of these I've already shown you. Nilus, and then there's thin snow on Nilus. Then snow, thick cold snow on thick sea ice. Thick melting snow on thick ice. That would be the situation in June. And then in the summer, drained bare ice with a surface scattering layer, and then the melt ponds, number 6. Then in the freeze-up time in September, you have refrozen melt ponds. And then, thin cold snow on thick ice is another possibility. Ice that remained bare through the summer, and then it starts getting snow. Okay, so to assess these glass bubbles, what do we need? For each let's see, here it is. For each of 8 surface types, we need the albedo of each type. We need the area covered in each month. We need the radiative properties of the glass bubbles. I'll show you that. We need the cloud climatology. Well, clouds reflect sunlight, so they limit the amount of sunlight reaching the sea ice. And then there's the solar flux for each month, and then we'll be using a 2-layer radiation model to put the layer of glass bubbles over whatever the surface is. So first, for each of 8 surface types, we got the albedo. And we're, oh dear. Okay, so this is a plot of albedo on the vertical axis as a function of wavelength on the horizontal axis, and the vertical dashed line that separates half of the sunlight that's in the ultraviolet and visible. The other half is in the near infrared. So the top one is albedo of snow. It's the brightest, and it's almost 100% at visible and ultraviolet. And then water is the lowest, about 7%, and everything else is in between. And these are from field measurements in the Arctic. And then we need the solar spectra also as a function of wavelength. And there's one for clear sky, one for overcast Arctic stratus clouds. And then those two, the albedo and the solar spectra, we multiply by each other, integrate over wavelength to get the overall average albedo for the solar spectrum. And we've done it then for these 8 different types, 2 of which are dominant in the spring, and 3 in the summer, and 2 in the winter, or rather in the autumn. And the highest albedo is for snow, 81% under clear sky, 87 under clouds, and the lowest is the open water, and the others are in between. Okay, so then the next thing we need is the area covered in each month. Sorry, I don't know what's happened here. But, okay, there we are. So we got these 8 different types, and then the months of the year where each type is occurs. So it's different times of year that you have the different types. So there's a percent of the area covered and then an uncertainty estimate. The most dominant of the 8 types are these 4. There's thick, cold snow on thick ice, thick melting snow on thick ice. There's bare melting sea ice, and then thin, cold snow on thick ice. And sorry about that. We need now the glass bubbles. What happens to light when it reaches a surface? There are 3 things that can happen. You can have reflection, you can have absorption in the layer, and you can have transmission through a layer. So a layer can do 3 things. Those 3 percentages have to add up to 100%, or 3 fractions add up to 1. And this is the plots of those values from 0 to 1 as a function of wavelength reported by the field group. So absorptance, well, reflectance and transmittance are shown here, and then this is the absorptance. And they, if you average over wavelength, you get 43% reflectance, 47% transmittance. That leaves 10% for absorptance. And it turns out that's extremely important, that 10% absorptance. We'll see. Yeah, so that white powder, it looks white, but it does have some absorptance. They absorb about 10%. Okay, then next, what do we need? We got, sorry about this, we need the cloud climatology. So clouds, they cover in the summer about 80% of the area. They have an albedo about 0.4, transmittance of 0.5. So you increase the surface albedo by 0.25, it'll only increase the top of atmosphere albedo by 0.1 because clouds are hiding the surface to some extent. But the incident sunlight at the top of atmosphere is about twice the surface value. So the radiative forcing at top of atmosphere turns out to be about the same as at the surface. Next, solar flux for each month. Okay, so here for the 12 months of the year at 5 different latitudes, the incident solar radiation. It gets as high as 500 watts per square meter in June at the North Pole. And there's a plot here at the bottom showing, over the course of the year at the top of atmosphere and at the surface, about twice as much at the top of the atmosphere as at the surface. Okay, then, okay, now we're going to put a layer of glass bubbles over the surface, which may be snow, maybe sea ice. And so the sunlight comes in, some of it gets through, some of it gets reflected by the glass bubbles. Some of it gets through and then hits the surface, and some of that gets reflected by the surface. And of that goes reflected, some of it gets through the layer of glass bubbles. Some of it doesn't. Some of it gets absorbed, some of it gets reflected back down. And then there's the possibility for another reflection, and so on. So it's an infinite series, and the infinite series has a sum. And the equation then to give the total reflectance, total albedo of the system, it's a function of the reflectance of the glass layer, reflectance of the ice, and the transmittance of the glass layer. Okay, so here's the result. So this is the black line. It shows what you get for albedo if you don't have any glass. In other words, the albedo is just the same as the surface albedo. So you've got the underlying albedo from 0 to 1, the system albedo of the surface plus the non-existent glass would just be this 1-to-1 line. Now look at the red line. The blue we'll come back to later on, but the red line shows the albedo with a layer 330 microns, so a third of a millimeter layer of glass bubbles. If you're over a black surface, it raises the albedo up to 0.42. So if it's a dark surface, you can make it brighter. But because these bubbles absorb some, if it's a very bright surface, actually you decrease the albedo. So if you have an albedo of 1, then it's going to lower the albedo. And at this key value of 0.61, there's no effect. In other words, that's the albedo of bare sea ice melting in the summer. So putting the glass bubbles has no effect there. So yeah, if it's a bright surface, you make it darker. If it's a dark surface, you make it brighter. And then if you make thicker layers, that was just for 1 layer, then if you go to 2 layers, 3, 4, 5, eventually you asymptote to an albedo of 0.61. Or if it's a white surface, it'll bring it down gradually to 0.61 if you add more and more layers. Now we go to the radiative forcing. This is in watts per square meter. Positive forcing means a warming. Negative forcing means a cooling. And so we have these big positive forcings because if you put the glass bubbles over snow, it's going to give a warming. And that's what this is. Snow, that's cold snow. The red ones are melting snow. And then you do have some cooling. In the spring, it's from this new nilus where you had open water exposed and then you've got new ice that hasn't yet gotten a snow cover on it. But these blue, we have an asterisk by them because that's the melt ponds. We did calculate them, but we're going to discount them because we think that you're not going to be able to maintain a uniform layer of the glass bubbles on the melt ponds. So you can see what's going to happen if you add up all the months and add up all the radiative forcings. The sum over the year is going to come out to be a warming. And indeed, if you add all the different the effects on all the different types together and ignore the melt ponds, then it's warming at the top of the atmosphere and at the surface. And its annual average is about 3 watts per square meter. So it's a positive forcing in March through June and very small in other months. And so our conclusion that we published, the net result is the opposite of what was intended. Spreading glass bubbles would warm the Arctic climate and speed the loss of sea ice. We also did calculations for an alternative material. Suppose the glass bubbles could be made not to be absorbing. And so a non-absorbing glass powder, so we say, because we found this result, we're going to say if glass bubbles are to be spread over the Arctic sea ice to raise its albedo, it will be necessary to manufacture non-absorbing glass bubbles. Maybe they could be manufactured, and assuming that they would be applied only once a year at a time when they would not immediately be covered by new snowfall and hidden, they should be applied during May, and then they'll be effective for the 4 months, May to August, and then they'll be covered and buried in the new snow. So now we've got this, we've got the yellow code for the result of non-absorbing glass bubbles. So indeed, they cause only a cooling. They cause a cooling particularly in the summer, and the result would be a negative forcing of 4.6 watts per square meter on the average. So there are 3 caveats. 1, could they be manufactured? Secondly, if they could be dispersed without contamination. Well, the way they were supposed to be dispersed is from a ship with a tall stack and just spewed out, and the wind would just carry them to be deposited on the ice. So the ship would have to make many transects. But of course, the exhaust from the ship's engine will be carried by the wind in exactly the same direction, and it contains black carbon, soot, from burning of diesel fuel. So it would be difficult to disperse without contamination. The other thing is that these glass bubbles are fragile, and they do break, and they sink. So if they would remain unbroken and wouldn't sink, you could get that. Anyway, suppose all those things could be overcome, how much would it cost? Well, you could get an average radiative forcing for the 4 months, May to August, 9 watts per square meter negative, or 3 watts per square meter on an annual average. It would require 360 megatons of glass bubbles. We could compare the radiative forcing caused by applying non-absorbing glass powder to what would be the positive forcing caused by removing all Arctic sea ice and replacing it just by ocean water, which is plus 21. So the gain what you would gain is 1/7 of the amount that you're trying to prevent. Now we did a comparison of the efficiency. Well, the efficiency is the radiative forcing per unit mass. How many watts per square meter per gigaton could you get? And so we got a number for that, and we compared it to the stratospheric aerosol injection, which has been estimated by others. There, they do it per megaton because that doesn't require as much. And we conclude cooling the climate by stratospheric aerosol injection is at least 1,000 times more efficient than by spreading the non-absorbing glass bubbles, if they could be made. Now, is that what we call an apples-to-apples comparison? No, it's a comparison of glass to sulfur, but we put it in the paper anyway. So to summarize, spreading the white powder over the Arctic Ocean would brighten dark surfaces, it would darken bright surfaces, and the net result is darkening, warming the Arctic. And so Melinda and I published that in the journal Earth's Future. To characterize it, I would say our work was a thorough assessment, but only of the radiative effect. There are additional considerations that must be addressed for this and other geoengineering projects. There's the feasibility and the cost at large-scale application. There's the toxicity and other hazards. And there's governance. How do you get permission to do any of this, or even to do a little test? Well, that ran into trouble. There were protests by the native Alaskans when the Arctic Ice Project wanted to do an experiment. I guess they did a little experiment on a lagoon at the north shore of Alaska. But there was a lot of protest just for that. And now, finally, we have some news. Actually, it came out in January. The Arctic Ice Project announced that they are concluding their research and winding down the organization. The members of that group have abandoned it. They're going on to do other things. The reason they gave was because ecotoxicological tests have revealed potential risks to the Arctic food chain. You can imagine the birds eating these glass bubbles. But maybe our work had some influence on that decision. Now, I want to advertise a paper that's going to be published, Safeguarding the Polar Regions from Dangerous Geoengineering. It considers 5 different proposals for geoengineering in the polar regions, some of which are not for climate, but are rather for putting a curtain under the ice shelves in Antarctica to prevent warm water from coming in and melting them. Anyway, considers 5 proposals and rejects them all. One of the projects they consider is the glass bubbles I've been talking about. And one of the authors is Professor Regina Hock. And when this paper is published, she will offer a seminar to present it. I also want to thank Regina for hosting me here for a month. That's all.
Great, thank you. So, questions. Do we have any questions? We have a microphone, so if you have a question about this.
Yeah, Terry.
Yeah?
Thanks for an interesting talk. You looked at the radiative forcing, but the heat that is absorbed by these bubbles, is it obvious that everything goes to melting the snow? Could it be radiated out to space so that you actually save some of the ice below? I mean, this absorbing heat, if that is going out as long wave radiation, is it obvious?
Yes, I only talked about solar radiation. Long wave radiation is equal in magnitude overall to solar radiation. That's an interesting topic, and how you think about it is, well, what you get depends on how you think about it. There even was a proposal, I just was reading about this morning, not that it ever got pursued, but one way of helping to cool the Arctic would be actually in the winter. If you could get rid of the ice only in the winter, then the ocean mix layer could rapidly cool to space. And so the presence of the ice in the winter, it's often in climate theory considered a, to have a cooling effect on the surface air temperature, but it actually has a warming effect on, or preserves the warming on the Arctic mix layer. Well, okay, so yeah, if you get a darker surface in the summer, yeah, it'll warm up. Well, actually, what'll happen in the summer, it won't warm. The surface in the Arctic Ocean in the summer is right at the melting temperature. So if you absorb more solar radiation, you don't warm the ice, you just melt it. And so until it's all gone, the temperature won't rise. I guess that's the short answer.
So the layer is so thin?
Oh.
So the layer of these bubbles are so thin so that the conductivity will immediately transfer the heat to the layer below.
Yeah.
It will not
escape. It's only 1/3 of a millimeter.
Yeah,
that's
so
something that we didn't calculate, but yeah, the heat will be conducted right through it.
Yeah, that's the assumption, or at least.
Yeah.
I mean, you mentioned too that the best time to do this would be in May, to spread it in May. But I'm guessing exactly this, that you would be melting a lot and then it would be going right into the ocean, right?
Yes.
Yeah. Which sounds like an environmental catastrophe, right? And we already know that seals have, PCBs and these kind of things, PCBs, and so now they're going to have glass beads in their bloodstream as well, in the fat, right?
What will happen with the reflection when the glass bubbles will go into the sea and lie like a soup in the sea? I will presume that it will, because it glass, it will sink, but it's so light that it will be traveling around with currents. And what will happen down there, do you think?
Okay, well, I don't think I can think about it any better than you can, but yeah, I'll move around with the currents, then they break and they'll fall to the bottom of the ocean and so on. And it's, studying these glass bubbles was not something I would have ever intended to work on. I just got pulled into it. It's a distasteful topic, I think.
Okay, any other questions? Okay, all right, let's, okay.
White paint, titanium oxide. That could also be a possibility.
White paint?
Did you get it? Titanium oxide. It's what you have in white painting.
Yeah, okay, titanium oxide, white paint, yeah. Actually, if your city is getting too hot, you can paint the roofs of the buildings, and that'll help cool within a city. Yeah, in fact, that's a useful thing to do, is to use paint to keep urban buildings cooler, reduce the energy needed for air conditioning in warmer climates. I guess you could paint roads also, but I don't know of any. I can't think of any use for natural surfaces.
How would you spray paint the Arctic?
You asking me? Yeah. I'm not going to do it.
Yeah.
Titanium oxide is a very common nanoparticle. It's used a lot.
Yeah.
The material I talked about is a very common nanoparticle. So they cover the titanium oxide with different substances in order to make effective nanoparticles.
But you still need to get it. You still need to spread it, right?
Yeah, but
Over all the ice.
it's the same size as this glass.
Okay.
I wouldn't do it, but
Okay, great. Thanks. Let's thank the speaker once again.